In my previous post, I introduced the subject vector space where I discussed some of the basic concepts, a few definitions, and discussed a theorem. Today, I am going to explain how vectors can be represented as matrices. First, let us consider a five-dimensional vector space that contains five basis vectors. The basis vectors are named as E1, E2, E3, E4 and E5. As we have already seen, any arbitrary vector v present in this space can be expressed in terms of these five basis vectors by the relation v is equal to summation of vi ei. I takes values from 1 to 5. Now here it is important to understand that the basis vector for a specific vector space is fixed. The difference between any two vectors lie in their components, whereas the basis vectors are remaining same if we are considering the same vector space. For example, let us consider two vectors v and v prime. They are expressed in terms of basis vectors as you can notice, for these two vectors, only their components are different while the basis vectors remaining same. Hence, in order to specify a vector in a given basis, only mentioning the values of their components are sufficient. The components are usually arranged in the form of a column in a matrix. In this way, a single column matrix can represent a vector. They are often called as column matrix or column vector. Similarly, in an n-dimensional vector space, a vector is represented by a single column matrix having n number of components. The basis vectors are also represented with column matrices. The matrix has n numbers of components equal to the dimension n of the vector space. Out of all these n components, only one that corresponds to that specific basis vector will have value 1. The values of the rest of the components are zeros. For example, if the basis vector is E2, then the second component will be 1 and the rest are zeros. Similarly, for the basis vector E4, only the fourth component will be 1 and the rest components are zeros. In this way, when a vector is represented as a column matrix, then it is called a Ket vector, and this specific symbol is used to indicate a Ket vector. Similarly, basis vectors are also represented with Ket vectors. The Hermitian conjugate of a cat can be obtained by performing a dagger operation on it. The dagger operation is actually a two-stage operation where first every component is replaced by its complex conjugate and then the transpose of this matrix is taken. As a result of the transpose operation, the column matrix is turned into a row matrix. This row matrix is another representation of the same vector v. This representation is called Bra vector and it is designated with this symbol. It is important to remember that when a vector v is represented as a cat, it is a column matrix whose components are same as the components of the vector, whereas when the same vector v is represented as a bra, it is a row matrix whose components are the complex conjugates of the components of the vector. As shown above, from a given cat vector, its corresponding bra vector can be obtained by performing the dagger operation. Now let us find out what happens when bra and ket vectors are multiplied. Let us consider a bra vector W and a ket vector V. The product is the result of a matrix multiplication of one row and one column matrix. The result as per the rule of matrix multiplication is, this result can be written as the summation of Wi Vi, where I goes from 1 to n. This term is known to give the inner product of the vector W and V. Thus, we have found that the product of a bra and a ket vector is the inner product between these vectors. After establishing this fact, let us now investigate the product between two basis vectors. As I said earlier, basis vectors are written as ket vectors like this. And a basis bra vector can be obtained from a basis ket vector by performing dagger operation. Take a ket V and a bra W. Let us write ket V in terms of the basis kets and the components of V. Also write bra W in terms of basis bras and the complex conjugates of the components of W. With these values, the product of bra W and ket V becomes summation of Wj star Vi multiplied with the inner product of two basis kets. Recall here now that we have just found out that the product of a bra and ket is same as the inner product between these two vectors. Therefore, the term must be equal to the summation of Wi star Vi. This happens only when the product of the basis bra and ket is equal to Kronecker delta. In this way, it is established that the inner product of two basis vectors is equal to Kronecker delta. This is an expected result because the basis vectors are orthonormal to each other. Now I shall explain a small trick to find the component of a ket vector. Let ket V is defined over the basis vectors Ej. So ket V can be written as the summation of Vj and ket Ej. Multiplying with bra Ei, we get this inner product between Ei and V. Just now we have seen that the inner product of two basis vectors is Kronecker delta. Hence the term becomes summation of Vj and Kronecker delta. Now notice carefully here that all the terms in the summation have different j values from 1 to n, whereas the value of I is fixed, only one value. Since I has only one fixed value, according to the properties of Kronecker delta, only that term in the summation will remain which has the value of j same as the fixed value of I. The rest terms vanish. Thus the term remaining is Vi, which is the ith component of V. In this way, multiplying ket V with bra Ei, we get Vi. We can state in general, whatever component of ket you want to find out, multiply the ket with the corresponding basis bra. It will result in that component of ket vector.